Okay, yeah. As I mentioned, today we have a lot of material, but I don't think it's gonna take us a long time. It's mainly just I summarized all different uh, face portrait theme. So I summarized everything for you. With your type. So if you have the eigenvalues, based on the eigenvalues, you can decide if it's if it's node, saddle point, or spiral source, spiral sink center. So I summarized everything for that, and I also put all the pictures in there. So when you do such questions, it's gonna be much easier. What are those things? I'm pretty sure you covered it in lecture already, right? The equilibrium solutions. Yeah, like nodes, nodal sink, nodal source, improper nodal source, saddle point, spiral point center. Oh no? Wait, what? Seriously? Hmm. That's interesting. Let me have a look. Because I designed my tutorial based on your lecture notes, and I saw those in your lecture notes. That's why I did it. Hmm. When is your lecture? You just finished Defective? So that means I am ahead of your lecture again. Uh, that's okay. I don't know what to say anymore, to be honest. Why are you guys so slow? I honestly don't know why you guys are so slow. But okay, let me read your chat. Chat is really active right now. Hmm. Question. I feel so bad for whoever's gonna mark question 3 on the problem set. What's question 3? For homework 7? Yes. Homework 7, question 3. Ah, this one. It's not bad. It's not bad. I marked so your question 2 and your question 3 were on the problem set last semester as well. And last semester they had 6 questions, including those 2, and I marked 5 of them. So I marked both of them. It didn't take me that long. Also, it's always Faja's gonna mark the first question, I mark the second question, and Amjad mark the third question. It's always gonna be like this, so it's not gonna change. So you basically know who's gonna mark which question already. It's not bad. What about the quiz? Oh, the quiz. It's because okay. Let me share my screen and then we can keep talking. So for the quiz, you have 5 quizzes, right? So basically, um, you is you have 5 quizzes, and we have 3 TAs only, but we have 2 professors as well. So basically, what we're doing is each of us will mark 1 quiz for both session. I mean, like so you have 2 sessions, so it's like 10 quizzes. So each of us will mark 2 quizzes, 1 for each section, and it's not. Yeah. So I marked. How many quizzes has I marked? I think I marked 2 quizzes already. So I have no more quiz marking. Or did I mark 2 quizzes? I don't remember. I think I marked 2 quizzes already. Yeah. And yeah, I think so. So I have no more quiz marking. Lee In, the prof Lee In, I think he wants to mark quiz 3 for his own session. So he's marking that. And I think, let me have a look. Not sure if he started yet. But he told me he wants to mark that, so. I think the rest of the quiz marking is gonna be the two of the professor. Yeah, he hasn't started yet. So the rest of the quiz marking is gonna be the professors and an MJet because he only marked one. So two quizzes will be marked by Natalia, two quizzes will be marked by Lane, and one will be marked by Amjad. Anyway, any other question before we start? Let's see. I don't know why Lane's session is so much slower. Yeah, looks really slow. I think they did it in different order. I think Natalia hasn't covered defective eigenvalues yet, and she went straight to face portrait, and Lee did defective eigenvalues first. So they're not doing in the same order. Yeah, it looks like it. Well, it doesn't really matter because I'm gonna do both today. And hopefully, if you haven't done this one, after today's tutorial, you know how to do this. And if you haven't done the face portrait one, it's really simple. Basically, I've spent most of my time creating this table, and so I created this today. I spent most of the time creating this. So with this chart, it should give you all the answers already. Yeah, so because I checked your textbook, they don't have that. So basically, what you need to do is you find the eigenvalue, okay, and fit in one of the category. It's either both positive or both negative or opposite side, or they are repeated. And if it's defective, you pick. So based on your eigenvalue and use the table I provided to you, you should be able to figure out the type and the stability. And using the type, you can go back to my, like starting from this page. Okay, using the chart, you can go back to page 3 to page whatever to look at the graph. So the graph is gonna be corresponding to the chart as well. So it's like a pretty good summary, I would say so. So after this, I think you should be good. Anyway, let's go back to the beginning. We have defective eigenvalues. What does this mean is what we actually did this before. This is when you have an eigenvalue with multiplicity that's greater than 1, okay, and it's not complete. What do I mean by not complete? It means that, well, the multiplicity is greater than 1, but you cannot find as many uh, linear independent eigenvectors as you should be able to find. So let's say if your multiplicity is 3, but you can only find 2 linear independent eigenvector, so you're missing one, then in that case, this eigenvalue, lambda, is called defective. Which we actually talked about it before, but we never did a complete question. Before I just tell you, oh, it's defective, or I didn't even use the word defective. I just said, oh, you cannot find as many eigenvectors as you should be able to find, so we need to use one of them to find the other one. So we actually talked about this before, except I never tell you that, well, what is gonna be a y1 and y2. So here it is. How to find an additional eigenvector with repeated eigenvalue where this eigenvalue is defective. So suppose a homogeneous linear system with repeated eigenvalues lambda 1, and lambda 1 gives only one eigenvectors. So that means that this lambda 1 has multiplicity that's greater than 1, but you can only find one eigenvector. Well, that's gonna give us one basic solution y1, right? So y1 is your eigenvector times e to the lambda 1t. To find the other solution, you just let this equals to your eigenvector. So the eigenvector you found before, you let it equals to that, and whatever you find, that's gonna be your lambda 2, and your lambda 2, where do I write it? So this lambda, not lambda 2, this eigenvector is gonna be say 1 t plus, so I used u here, so u, I'll just use u. So u is your second eigenvector. U is your second eigenvector equals to whatever you found. So the second one you found. Okay, so that's your u. Actually, this looks ugly. Don't use this. Just use this formula because it's making it more confusing. Yeah, so it's gonna be the first eigenvector times t times e to the lambda 1t plus u, which is whatever you found from here, e to the lambda 1t. So here is an example. As always, I'll give you some time to work on this example, and we'll take it up. If you want, you can write on the board as well, just annotate. Did you get your ball?
Yeah. It's so cute. I sat down. He sat next to me, and then he's like, so cute.
Right. Sit. Hello? Did you just ignore me? Brownie? Brownie, come back. Come back. Come back. Sit. Sit. No, this is coffee, not for you. Anyone wanna write on the board? I think it's pretty straightforward, as long as you can find eigenvalue and eigenvector. It will be pretty messy if I annotate. Okay, anyone else wants to do it? Or in the exam, the question usually are 2 by 2 or 3 by 3. I don't know. Let me check the exam from last semester. I actually don't know. Yeah, it's really messy. And I don't think it's necessary to give you 3 by 3. But what I think doesn't really matter. It's what your professor think. So last semester they were given one 3 by 3 matrix, but the rest are 2 by 2. Yeah. So it's not too bad. At least they didn't give you 4 by 4 matrix. Oh, speaking of this, I took MAT244, linear algebra 2 at St. George. And on my final exam, I was given an 8 by 8 matrix for one of the question, and I was like, oof, spent so much time on that 8 by 8 matrix. Yeah, it's like half of a page is gone because of the matrix. It's not computation, so because it's a proof course, so it's not about computation, it's something else. But making it 8 by 8 matrix was like gonna make our life much harder. But it was a 8 by 8 matrix, and I literally laughed during my exam because I was like, I didn't expect this. So 3 by 3 matrix is actually not bad. Okay, can someone tell me what's my eigenvalue? And what is the multiplicity of this? I'm not gonna do the computation. Someone tell me what's my eigenvalue? Lambda equals to -3, okay? And multiplicity 2, okay? Multiplicity 2. So let's find the eigenvector. 6, -18, right? And then 2, -6, 0, 0. And this will give you 1, -3, 0, 0, 0, 0. So that means my first eigenvector is gonna be 3, 1. Okay, so y1 equals to 3, 1 e to the power of -3t. That's my y1. And using this, we can find y2. So a minus lambda I, let's see, u equals to 3, 1. So that matrix is gonna be this, except we change 0, 0 to 3, 1. So this will give us 1, -3, 0, 0. And here is 1 over 2 and 0. So that means my u is gonna be 1 over 2, 0 plus 3, 1 t. So my y2 is gonna be 3, 1 t to the e to the -3t plus e to the -3t times this. So 1 over 2, 0 plus 3, 1 t. Any question? Or did I make a mistake? X2 is V1t. Makes sense? And the general solution is, well, you add C1 and C2 in there. It's a linear combination of those. Okay, cool. The next one, let's talk about equilibrium solution. So the next probably 10 to 20 minutes, it's just gonna be me talking. But I think it should be really helpful, because when I took the course, I wish someone could summarize for me. So I summarized for you guys, so you don't have to wish you have it already. Anyway, equilibrium solutions. Consider the first order linear homogeneous system, x prime equals to ax. The equilibrium solution is when this equals to 0. So it's when the first derivative equals to 0. It's, or it's called equilibrium solution or critical points, which we actually talked about it before, but before we did not classify it. If A is singular, which is determinant is not zero, then the only equilibrium solution is y equals to zero, which you guys should know this by now. Phase plane and phase portrait, if we denote the solution x equals to x1t, x2t, then we can plot x1t and x2t as a parametric curves in the x1, x2 plane. And this plane is called the phase plane, and the curves are called the phase portrait, which you should know if you're in Natalia's session. If not, well, now you know. And we have 5 different cases for classifying the equilibrium solutions. So the first one is when your eigenvalues are real, distinct, and they have the same sign. Same sign means they are either both positive or both negative. Okay, so that's called node, and depends on if your sign is both positive or both negative. If it's positive, it's called nodal source. If it's negative, it's called nodal sink. So positive is source and negative means it's sink. And the second one is saddle point, is when your eigenvalues are real and they're different. So they are distinct, and also they have opposite sign, which means one is positive and the other one is negative. The third one is called proper node. This is when you have repeated eigenvalue and 2 linear independent eigenvector, which means you have repeated eigenvalue but it's not defective. Okay? Or if you have repeated eigenvalue and it's defective, then it's called improper node. And they look different as well. So I'll show you the graph later. The fourth one is when you have complex eigenvalues, but it's complex but it's not purely imaginary. Okay, so if you have alpha plus beta I, this one is when your alpha does not equal to 0. It can be positive or negative. And again, if it's positive, you have spiral source. If it's negative, you have spiral sink. Okay, and when your alpha equals to 0, then you have pure imaginary eigenvalues, and this is called center. So we'll look at each one in detail. The first one is called nodes, where your eigenvalues are real, distinct, and they have the same sign, and this is a general solution. So if you look at, you can read all those in your own time. I'm not gonna repeat them. So if you look at those two graphs, those two are nodes, okay? And based on those two graphs, which one is proper, which one is sink and which one is source? Anyone? Left one is what? Left source, right sink. Yes, so remember source means you're going out. Okay, it's a source, so that means it's like, so this one is source, exactly, and this one is sink. It's sinking in, source is coming out. So this one is the full name, I think it's improper nodal source and improper nodal sink. So let's write it down. Improper nodal source and improper nodal sink. Okay, so that is the first one. This is one. Remember, this is when your eigenvalues are real, distinct, and they have the same sign. And source means they have. So source means they are positive. The same sign, they're both positive, and sink means they are negative. So they are both negative. And the graph looks like this. Okay, so if you're asking to graph it, it should look like something like this. The second case is when they are real distinct but they have opposite sign, which means one is positive, the other one is negative, and that graph should look like this. So this is called saddle point. And those things you should read it yourself. So it's like tell you how to draw the graph when you are given, let's say um, when you have your constant and when you have your eigenvector. So this is like specifically how you draw it, but generally it looks like this. Okay. And the third one, 3a, you would have proper node. This is when you have repeated eigenvalue. However, they are not defective, which means if you have multiplicity of 2, then you can find 2 linear independent eigenvector. So this is called proper nodes. Another name of it, it's called star point because it's like straight line going either in or out. So it's also called star point. Okay. And as always, you could have positive or negative. If it's positive, it's proper nodal source. If it's negative, then it's proper nodal sink. So again, positive is source, negative is sink. So the graph should looks like something like this. And then you would have improper node. This is when you have defective eigenvalues, which means you have multiplicity greater than 1, but you can only find one eigenvector. One linear independent eigenvector. So in that case, it's called improper node. And also based on your eigenvalue, if it's positive, where is it? If it's positive, it's called source, and if it's negative, it's called sink. So this is sink. So improper nodal sink, and this is improper. Are they both sink? Yeah, they're both sink. I should have put the source here, but I just realized they're all sink. Anyway, yeah. Source is just going out. So next one, spiral point, you have complex eigenvalues where your real part is not 0. So those you can read yourself. This is what it looks like. You have spiral source, which means your real part is positive. So positive real part. Okay, and if your real part is negative, then it's called spiral sink. So see the arrows, this they're going in, right, and this is going out. Anyway, and lastly, when your real part equals to 0, then it's called center. It's like a lollipop here, see? Yeah. So center is just center. There is no positive or negative involved because it's imaginary. And that's everything. And here is a chart. So spend a lot of time on this. Hopefully it's gonna be helpful. So based on your eigenvalue, okay, so you can tell that the type of those, okay, and then the stability of those. I checked your textbook and your lecture. They didn't talk about asymptotically stable, but I'll just tell you that it's a kind of stable. So you can just call it stable if you want to. So it's just stable and unstable, but this one is, it's one type of stable, and I want to explain what's the difference between the just stable and asymptotically stable. But for now, for this chart, when you put stable or unstable, you can ignore the asymptotically. Okay, because I checked your lecture notes. I don't think they talk about it unless I missed something. Did Natalia talk about this? Or she just used stable or unstable? Anyone remember? Yeah, that's what I thought too. So you don't have to know this. For now, you don't have to know this. Eventually, you might need to know this when we talk about locally linear system. But right now, I don't think you need to know. You just need to know that, well, it's stable. When I put asymptotically stable, it's just stable. However, although she didn't really talk about this, I will still talk about this and I'll tell you what is the difference between those two. I think eventually they will talk about it, probably next week or the week after. So here are the graphic representation of asymptotically stability and stability. So if you look at this graph, okay, if you look at this graph, you'll see that, where do I start? A is called asymptotically stable and B is called stable. Okay, you'll see that this is where you want to reach. So, actually, how do I say this? Did they talk about the definition of stable and unstable? Or no? No? Like, not even a definition. The. To be honest, you don't know. Like, the limit definition. You don't think so? Then I don't know if I need to talk about this. I with equilibrium point, you think? You're kind of lost when I tell you I was going to. Okay. Okay, so I'll tell you about this. So this is stable. This is stable. So basically, stable. I'm not gonna give you a formal definition because your professor haven't done it yet. So you do it later. But stable means that the trajectory of the solution is gonna be around the critical point. So like this, it's gonna be around it, but the thing is that it never reaches it. So it's like going around this. Okay? So it's gonna be approaching this, but it's never gonna be here. That's stable. Does that make sense? Like, remember before we talk about stability, I said, well, if your solution curve is approaching your critical point, then it's stable. If it's going away from your critical point, then it's unstable. Remember we talked about that and we draw the graph? I'll show you. Don't remember where it is, but we'll see. It was somewhere exact equilibrium. Yeah, right here. So intuitively, this is what happens. So like remember when we talk about stability, you have it's either approaching your critical point or it moves away from your critical point. Yeah, exactly. So remember when we talk about here, I said, well, the solution curve is going towards your uh towards your critical point, that's why it's stable. And when it moves away from your critical point, it's unstable. Right now, I want to talk about the difference between stable and asymptotically stable. So for stable, it never reaches it. Can you guys tell? It's going around it, but it never reached the point. Okay? But for asymptotically stable, it's going around it, but eventually, so as t goes to infinity, okay, it's gonna get there. So eventually, it's gonna approach your critical point as t goes to infinity. That's the difference between those two. Does that make sense? So it's like the graph here. Brownie, calm down. Yeah, okay. So I hope this cleared up everything. But again, you see that, well, this is one kind of stable because it's approaching the critical point, right? So it's also one kind of stable. Anyway, example 2, I want you to sketch the phase portrait and classify the critical point of the system. So I'll give you some time. If you want, you can sketch it yourself. Actually, sketching might take too long, because let's just classify it instead of sketching it, because that might take too long. As long as you know what it should look like, it's okay. So let's just classify it. How do I? Someone said, how do I sketch it? You classify it and sketch your graph based on what we did before. Like, for example, if it's center, it should look like something like this, and it depends on, oh my god, Brownie, and it depends on your eigenvector. So it should have really small difference, depends on your eigenvector. But let's just classify them. I haven't seen they ask you to sketch it for this course. They just ask you to classify it, so it should be okay. Brownie, we're doing 2. Oh, sorry, 2. Oh. When I say classify it, you should tell me if it's stable or unstable as well, okay? Brownie. Can you guys hear my dog panting here? Yeah, it's like really annoying right now. It's not letting me go. Right. Stop. Do you guys want to see him? I can't turn on my camera. Okay, cool. Right. No. It's not even letting me touch my laptop. Here. Say hi, Brownie. Brownie, say hi to everyone. He's huge. He's a big boy. He's like almost 40 kilograms now. 38 or 9, the last time we checked. Brownie. Yeah. Let me go. Brownie. Yeah, he's a huge boy. Yeah, I don't think I can write anymore, so we'll probably just talk because he's not letting me write anything. Unless one of you want to write down something, I don't think I can do it anymore. Brownie. Should be pretty simple. As long as you find your eigenvalue. So someone write it on the board. Okay, it seems like we have lambda being -2 with multiplicity 2. Ooh, see, he's standing up. Oh, you're so heavy. You're so heavy. Oh, Ronnie. Okay, go away. Let me write down. So lambda 1 equals to lambda 2 equals to, wait, what does it equal to? -2? And is it defective or no? How many eigenvector can you find? Linear independent eigenvector can you find? One. Everyone agree with this? Because I didn't do this. I'm not sure. I'm actually not sure. What does that mean? How many linear independent eigenvector can you find using this eigenvalue? Okay, so let's go back to the chart. So -1 means that -2 means that they are both negative. So that's gonna be this one. Gonna be yeah, I can't draw. Someone draw it for me. It's gonna be this one. Okay, and then now you decide if it's defective or not. And you guys said it's defective, so it's gonna be improper nodal sync. So this one, okay? Any question? You didn't get the same thing? Oh, do I need to? Okay, then let me do it using I'll do it using matrix calculator because I don't think I can do it right now. What is it? -2 1. Brownie. Let's see. -2 1 0 -2. So eigenvalue is -2, and then it's defective. So yeah, you're right. So it's defective. So that means eigenvalue -2, and it's defective. So it's improper nodal sync and it's asymptotically stable. Okay, so the first one is this. Now example 3. Ronnie. You have 3 dogs? Wow! Show us. Are they big or small? Because I don't think I can keep 3 big dogs. Like 3 tiny dogs might be okay, but 3 big dogs is like, and he's a mixture of Bernese Mountain and Golden Retriever, and he's like huge. Yeah, fine. Show us our picture. Oh, do you guys want to see my cat as well? Let me go find my cat while you guys do this example. No, where are you? No. No. Oh, where's now? I actually don't know where my cat is. I'll go find him. Is now here? I don't see him. Oh, here. Right here. There we go. There is my cat. Yeah, he was in the closet. He likes to stay in the closet. Nene, say hi. My cat and my dog doesn't get along with each other. Here. They really don't get along. Decide every day. I have no idea. I adopted him, so really don't know what breed. Anyway, back to this, guys. What eigenvalues did you guys get? And what eigen 2? Multiplicity 2? Okay, so lambda 1 equals to lambda 2 equals to 2. Is it defective or no? How many eigenvectors can you find? No, okay, so not defective. So not defective means we're looking at, so now it's greater than 0. Greater than 0, not defective, so it's proper nodal source, and it's unstable. Copy. So it's unstable, proper nodal source. Okay, that's 3. Let's do 4. Again, I'll give you some time. Try 4. I found him. I put him on the cat tree now. Let's see. Anyone got this? If we get the 0 matrix, what would it be? What do you mean 0 matrix? Like 0, 0, 0 everywhere? Yes, you should get. Yes, you should get 2 free variables. Yes, exactly. And that makes your eigenvector 1, 0, and 0, 1. Yeah, that's correct. So this one, what's it called? Wait, this one. For question 4, you get lambda. Question 4, -2. Wait, -2 and 1. So lambda 1, -2, lambda 2 is 1. So what is it called? They are opposite sign, so it's saddle point. Is saddle point stable or unstable? Anyone remember? Unstable, exactly. Okay. Unstable. Okay, I think that's it. So that's the end of the tutorial. Oh, you might change the matrix to something else and give you complex ones as well, but it should be straightforward because you have this chat. So make use of this table. And that's it. That's the end of this tutorial. I will see you guys next week.